afternoon, everybody, and thank you for calling in. Topic for today, I want to talk about kind of a safety aspect typically involved with supply systems and supply systems that are pressurized. And that has to do with liquid compressibility. So let's look at some of the very basic physics that underlie this. Okay, so right here, let's imagine we have a tank, cylinder, pressure vessel, whatever, and we fill it with liquid all the way to the top, vent out all the gas, and valve it in. So essentially it's closed. So no danger here. You basically just have a pressure vessel that's completely full of liquid. And it's at no internal pressure. It's at room temperature or whatever temperature it was that you filled it. Now what happens is the temperature is increased. And it doesn't matter how you do that. It could be that you literally heat these walls up. It could just be atmospheric heating. It could be still generated heat acting on this liquid. Could be a couple of things. If the temperature inside here goes up 100 degrees Fahrenheit, it's not really that much. The internal pressure can build up as high as 500 psi. All right, now that's kind of non-intuitive. You would think as the temperature goes up, maybe just get hotter. You wouldn't expect it that the pressure would increase up that much, but it does. The reason it does that is because even though we think of liquid as being incompressible, mostly in undergrad engineering school, you're taught liquid is incompressible, which makes it easy. You can cross out a lot of terms in some different equation derivations, but in effect, it's not. There is some slight compressibility to almost all liquids. That has to do with just, the atomic spacing of the molecules and some other things. And so it can compress just a little bit. And the other thing is we tend to say that it doesn't have any coefficient of volumetric expansion, meaning as we increase the temperature, the volume of it, barely increases at all, almost inappreciably. And that's true. That's true. It's very, very slight. But when you combine those two things, number one, the coefficient of volumetric expansion with compressibility, what happens is if you have what's called a closed system or a solid system, meaning there's no compressible piece to this, what happens is as the temperature rises, this volume wants to expand just a little bit. And also, since it's compressible, the volumetric expansion cannot happen because of the infinitely solid walls, if you will, of the pressure vessel. So what that means is all that energy goes into pressure production. And that's how you get that internal pressure of 500 psig. Now, in reality, the vessel walls are not infinite. So if the vessel walls expand just a little bit, they can help decrease this pressure somewhat, but not completely. And the thing about going solid in liquid systems is really from a pressure vessel standpoint, you almost have to assume that the stresses in the walls are infinite. And that is because such small changes in liquid volume can have such big changes in pressure. A little bit of history. Most of us have heard about 3 Mile Island and the meltdown that happened there. Kind of at the basis of that accident, those nuclear reactors what are called a pressurized water reactor, and that means you can look that up. It's called a PWR, and they have to have a pressurizer, which is basically a big compressible volume of gas, so that when the water is heated up by the nuclear reaction, and it's going to expand a little bit. You don't want that to burst all the pipes. So, and that's called going solid. And the engineers on site have been trained to not ever let that pressurizer go solid. And you can see why, and that's because you would generate extreme pressures in the extreme stresses in the sidewalls of the pressurizer and could probably rupture it. And so they had been trained over and over again, don't ever let that pressurizer go solid. Now we understand why. The problem is the pressurizer was not going solid, and by reducing the water volume in the system, what they were doing is reducing the amount of cooling water available to modulate the reaction, keep the temperatures reasonable. So it was their fear of going solid and some bad instrumentation that led them to essentially cut the cooling to the reactor. So in a couple of sentences, that's what 3 Mile Island was all about. They were afraid of going solid. Okay, so that's kind of on a huge scale, but nonetheless, it affects us. And the question is how? Well, let me save my cursor here. In 3 ways. We're going to look at just a typical plan 53A, we're going to look at a 53B, and we're going to look at a 53C. Now, as you can see there over on the left, this is just a typical pressurized 53A. What's important is this volume up here is gas, and it's almost always nitrogen gas. And by pressurizing this nitrogen gas, externally up here, then it acts directly on this liquid and it pressurizes the liquid. Now, all of our customers are trained to fill this to the normal liquid level before they start pressurizing it. There have been cases where customers say, I don't want to come out here and refill this when the seal's leaking, so I'm going to just fill it up all the way. Okay, if you fill this up all the way, you have now gone solid. And once you valve all this in, if you increase the temperature of the liquid in here, even by a little bit, the pressure inside this vessel will start to rise, and it will rise in an uncontrolled way. And yeah, the pressure gauge is going to tell you it's rising. The problem is it's going to rise very quickly. And so what is the heat that causes this fluid to expand? The heat is typically what we normally see in seals, and that is seal-generated heat and heat soak. Now, you probably wouldn't see an increase of 100 degrees Fahrenheit that leads to that 500 PSI condition, but it would not be unusual to see a 10, 15, or 20 degree rise, and that's going to create quite a hydraulic pressure and stresses in these walls, and conceivably you could exceed the MAWP of the reservoir and cause an unsafe condition. Now, one thing about this, the unsafety is not that the vessel will explode and send barrier fluid all over the plant and send metal parts flying. It's not an explosion like that, because what we said is that liquid expansion generates very high pressures, but again, that it does that in a very, very small volumetric expansion. So as soon as you get a leak or a puncture in this tank, it immediately relieves all of the pressure inside here. And so that means if it were to say, break through this weld or, puncture a fitting, you would have a very slight, maybe a spray, and then maybe a few drips, and then a complete loss of pressure. And you'd probably drain this out just up to the head level. So the danger is liquid escaping just from a rupture of the pipe, not like a big dramatic explosion where things go flying all over the place. Okay, so in this case, since you overfilled it and then you expose it to heat, you'll get pressure buildup in here, and that is a bit uncontrolled and not what you want. I did have one engineer tell me that that would be a really cool way to increase your barrier pressure without having to use nitrogen, which is just ridiculous. It'd be a truly ridiculous way to do it, and unsafe as you could imagine. Creative, but that kind of thinking needs to get back in the box, if you will. Okay, second instance, this is a Plan 53B. And if you're familiar with the 53B, what you have is, this is your barrier fluid in kind of this blue and green. And what happens is you charge this bladder. It kind of looks like a football. You charge it with nitrogen gas up to some pressure, and then what you do is you add the barrier fluid liquid to it. And as you add this liquid, you reduce the volume of the bladder, which means you start to pressurize the bladder beyond the initial charge pressure. And as you do that, you slightly decrease the volume of the bladder. Now, what can happen is over time, these bladders can get kind of brittle. If you're pressure cycling them and changing its shape often, you can get little tiny pinholes in it. And what that means is over time, you can lose the precharge. I mean, this is kind of looks awful here, but if you lose this precharge, then you have done what? You have gone solid. And that means you have no compressibility in the system. And in this case, if you were to heat up the barrier fluid in the whole system, you could start to develop pressures that were unpredicted and unpredictable. So that's why it's important to every time, on a maintenance schedule, what they need to do is block in the bladder accumulator so that you don't lose barrier pressure, block it in, and so you isolate it. And then there's usually like a little bleed valve in here so you can just bleed out this liquid. And then what happens is you pull all this liquid out of here, and this bladder should return to its initial precharge pressure. If it just dumps and goes to zero, that bladder is damaged, and you have no more compressibility left in the system. So that's something that you definitely want to watch out for with Plant 53Bs, because a lot of customers don't understand how they work. And of course, you can't see through them. You might not even know that a bladder's there. Some customers think when you inflate that bladder, you're actually pressurizing the barrier fluid as you do it. That's not true. What you're doing is adding some compressibility to the system. Final case, this is a Plant 53C. We don't use a lot of these, but there's a lot out there. And they're often used in fairly critical services in smaller pumps. Some ANSI pumps that have, pressures that really vary over time for the process. We want a barrier pressure that's not at a singular high value, but a barrier pressure that tracks that process pressure. And we do that with this piston multiplier. We call them a DRU. And what's important is when it's the same thing. This is the process fluid right here in red. And what you do is you manually pressurize the barrier pressure here in green and blue. You manually pressurize that by adding fluid until this piston gets to this maximum value. You kind of think of this as upside down. You see minimum on the top and maximum on the bottom. That means when I run out of barrier fluid due to leakage, this piston is going to rise. And then when it hits this minimum, that means you're at the minimum amount of barrier fluid. When you initially fill it and you're pushing this piston down, down, down until you hit this max, and then you need to stop there. If you don't stop there, what happens is you will push this piston all the way to the bottom. Once you push this piston all the way to the bottom, and then you were to start the pump, what would happen is any seal-generated heat in the barrier fluid has no compressibility function in here anywhere. And so once it bottoms this piston out, you have now gone solid. And that happens from time to time. And it's the same idea that I don't want to go out there and refill this thing every so often because seals leak. So what I'm going to do is I'm going to fill it all the way past the max until I can't even see the piston anymore. That's analogous to what that same operator did with the bladder, or with the not with the bladder, but with the 53A tank. And so they overfilled it, displaced all of the compressible portion. In this case, the compressible portion would be the piston and its ability to move up and down. And again, once you've completely filled this, what you've done is pinned it against the wall. You have no more compressibility in the system, and your seal-generated heat can really get away from you. Something that's interesting, I've seen one instance of this a couple of years ago where it was kind of a runaway reaction, if you will, because what happened was, as this was locked out, seal generated heat began to increase the pressure here, and in kind of an uncontrolled way. As it increased the pressure, the seal generated heat went up. Okay, that makes sense. As the seal generated heat went up, the temperature goes up. As the temperature goes up, the barrier pressure goes up, and it kept doing this. It kept feeding on itself. That's a process that's called autocatalytic, meaning the products of the reaction become the reactants themselves. And it just kept going and going and going until eventually this whole system held. But what happens is it blew the seals out, because the seals can only take so much pressure. And what we found was the pressure and seal generated heat got so high that the antimony and the antimony carbon actually melted out, which is at a really high temperature. And something interesting, we found that molten antimony is actually a really good face lubricant. And that's why we were able to go to such high pressures without really destroying the carbon. And it was the silicon carbide seat that fractured. So kind of interesting there. But again, please don't think this is a way to create barrier pressure by overfilling something and then heating it up. I hope that makes sense. So that's what you want to avoid is zero compressibility in the system. I hope you understand some of the physics going on now. And thanks for calling in. Have a good day. Talk to you later.